Hello students, how are you all? Welcome back to Akshar IIT Foundation classes. I am your chemistry faculty S. Mohan. So, grade 9 IIT Foundation, in this we started the second chapter of volume 2 isomerism, right? And in that we completed the first synopsis in which we discussed that isomerism, once just revising, isomerism means what? Two or more compounds having same molecular formula but a different properties are called isomers. That phenomena is called isomerism, right? This we studied. And then isomerism is mainly classified into two types that we discussed. One is called structural isomerism, second one is called stereoisomerism, right? In the structural isomerism, again we discussed 5 types of isomerism. Did you remember? Yeah. Position isomerism, chain isomerism, functional isomerism, metamerism, tautomerism. Okay. These all we discussed, right? In the synopsis one. So students, that isomers, structural isomers are very easy and that we completed. Right. Today, in the synopsis 2 of isomerism, we are going to discuss mainly about the stereoisomerism. What it is? A stereoisomerism. So, stereoisomerism is a little difficult, little not more difficult to understand, okay? Because that is for your level, okay? Because you are in 9th class level, okay? So, here it will be it will be difficult, okay, to understand if you don't concentrate, okay. So you have to concentrate, and then what I'll explain immediately you have to note down and listen carefully, concentrate, and try to understand it and practice, okay. So then the stereoisomerism, the second part of isomerism, becomes easy. Otherwise students, it will be very difficult, okay. So complete concentration of your mind, okay, here is required, okay. If it is possible, just 1 minute, close your eyes and take the meditation completely. Immediately you sit and bring complete your mind, brain, concentration to my explanation, okay. So then it will be easy for you. Is it clear? So just take 1 minute time. So now let's start. And if you have a material, open the page number 93, because wherever it is necessary, you open it and underline also. So here today I am going to discuss about the stereoisomerism. Stereoisomerism, right? So students, here stereoisomerism means what? Isomer, same, already same definition. The compounds having same molecular formula, okay, but differ in the properties. That isomers, and that phenomenon is called isomerism. But here little we change the definition, okay. So how can we define compounds having same molecular formula? Compounds having same molecular formula, and see, very important here, same structure also, okay, same structure also will be same. There in the structural isomerism, what we discussed, structures is different. Compound molecular formula is same, but structures are different. But here structures also same. Then where is the difference? But okay, difference in the spatial arrangement, okay, are called stereoisomers, and the phenomena is called the stereoisomerism. That's all. Very simple. No. Compounds having same molecular formula same, structure is also same, okay, but a difference in the spatial arrangement. Now you confuse. Structure same, formula same, how it would be spatial arrangement, okay. What is the spatial arrangement? Okay, that I will discuss one by one. I'll discuss. So be careful and listen carefully. Okay. Acha. So before going to that, so here in the last class we discussed that structural isomerism, stereoisomerism. Again, structural isomerism is divided into like 5 types like position, chain, functional isomerism and so on. So here also we are going to divide the stereoisomerism. So first we draw the stereo, okay, isomerism. Okay, in the stereoisomerism, mainly classified into 2 types. So see in your material, one is called configurational isomerism and second is called conformational isomerism. Okay, so first one is what? Configurational. Okay, configurational isomerism, and the second one is called conformational. Okay, conformational isomerism. Okay, like these 2 types are there: configurational isomerism and conformational isomerism. Okay, see here configurational isomerism, and second one is what? Conformational isomerism. Right? So now configurational isomerism, which is there, again it is divided into 2 types. Okay, configurational isomerism is again divided into 2 types. Okay, one are called enantiomers. This is not given in your textbook. Okay, enantiomers in your material is not given. Enantiomers. Okay, and the second one is called diastereomers. Stereomers. Okay, so these are again 2 types of them. Students, see, observe carefully here. Here configurational and conformational. Okay, configurational and conformational. Configurational, again 2 types are there called enantiomers and diastereomers. This in your material actually it's not given. So that's what I am once again stressing you, that enantiomers and diastereomers are again 2 types are there. Now when you come to the diastereomers, okay, again there are 2 types are there. Okay, one is called geometrical. Okay, so this is given to you directly. It is given geometrical isomerism and optical isomerism is given in your material. Okay, no problem. So here what they did is they removed this part. This part is not there in your material. Okay, so we need not to worry about this one. So whenever it is necessary, we discuss. So here it is given in your textbook, the material stereoisomerism, that is divided into configurational and conformational. And now this configurational again divided into geometrical and optical isomerism. Okay, because as you are in 9th class, only this part is given. But if you go to the higher classes, then what happens here? You can see, and if you go to the higher classes, what happens? Stereoisomerism, which is divided into configurational and conformational isomerism. Configuration again enantiomers and diastereomers. Diastereomers again classified into geometrical and optical isomers. So this today we are going to discuss. So many types of this, so a lot of confusion will be there. So that's what, so slowly try to understand. So we are discussing the stereoisomerism, in that configurational, conformational. Configurational, so enantiomers and diastereomers. Under the diastereomers again geometrical and optical. So here we are not going to discuss more about the enantiomers and diastereomers. Directly configuration. From configuration we go to the geometrical and then we come to the optical isomerism. Clear? So now what I do to remove your confusion, then I will remove this part. This part according to material. So then it comes like this. Configurational is divided into geometrical and optical isomerism. Clear? Sure. Now we'll discuss with the one example and each and everything. So open the material, page number 93. Now first we discuss about the configurational isomers means what, and conformational isomers means what. Right. So see here, configurational isomers means what? The isomerism which arises due to the difference in the spatial arrangement. Difference in the spatial arrangement. So here it is here, difference in the spatial arrangement. 1 minute. So difference in the spatial arrangement. This is still here it is same, but the thing is that they are not interconvertible. They are not interconvertible. Now see here, I will give one example so you can understand. Students, here For example, if you take one example, if there is one example like carbon, double bond, carbon, and here you take chlorine, here you take hydrogen, here you can take chlorine, okay, no problem, here you take hydrogen, okay. So now this is one compound. This compound is what you call the name to this one, okay. Now try to give the name of this one is what? How many carbons are there? 2 carbons, right? So 2 carbons is what? Eth, you know that 2 carbons is what? Eth, right? And here between which bond is there? Double bond, means what? Ene, okay. So that is ene, so ene, right? And now for if you take 1 carbon or 2 carbons are there. For first carbon also 1 chlorine is there, for second carbon also 1 chlorine is there. So total 2 carbons are there. So 2, where were the first 1 and 2? So 1, 2. Total how many chlorines are there? 2 chlorines. So this is called 1,2 dichloroethene. Okay, what it is called? 1,2 dichloroethene, right? Okay. So now students here, observe carefully here. Now this is the structure, 2 carbons are there. For these 2 carbons, for one side only, here chlorine is there, chlorine and chlorine, okay. The other side hydrogen and hydrogen is there. Now for example, I want to bring this chlorine here, I want to take this hydrogen there, means what? I would like to write the structure in this format, okay. So now see here, carbon, double bond, C, here chlorine, here hydrogen, here chlorine is there, but I want to take hydrogen here and I want to bring chlorine here, okay. So now you say, can I rotate like this? Here I am rotating like this so that this hydrogen is going up and chlorine is coming down, if I rotate, okay. So this rotation, is it possible or not? So on rotating like this, see chlorine, hydrogen, chlorine, this is same. But if I rotate like this, then what happens? This hydrogen goes there, this chlorine comes here, okay. If I rotate, then this structure, only this carbon I am rotating, if I rotate like this, I will get this structure, okay. See, what's the name of this name? What's the name of this one? That also we discuss. Now what's the name of this one? You see, how many carbons? 2 carbons. 2 carbons is called eth, okay. And between which bond is there? Double bond, so ene. And here this is the first carbon, second carbon. First carbon 1 chlorine is there, second carbon 1 chlorine is there. So 1, 2. Okay. So total number of chlorines are 2. So dichloro. Okay. The name of this one is 1,2 dichloroethane. What is the name of this one? 1,2 dichloroethane. See now. Both are having same formula. Okay. So same formula and the same structures also, if you see. Okay. Now this is called spatial arrangement. Spatial arrangement is what here see here. 2 carbons for 1 carbon hydrogen chlorine, 1 carbon hydrogen chlorine, so other carbon also hydrogen chlorine, for other carbon also hydrogen chlorine. Same. Okay. So formula same, structure same, everything is same. Where is the difference? Spatial arrangement. Here if you see 2 chlorines are one side of the carbon. See here one side only there. But here carbons are chlorines, okay, are same side, but here chlorines are opposite. Clear? So spatial arrangement, that's called spatial, difference in the spatial. Now, our question is what? Here this is there. If I turn like this structure will come. This hydrogen go there, chlorine will come here. Is it possible here? Can you able to rotate it? The answer is no. Yes or no? The answer is no. Why no, sir? Just rotating, no. Can't I rotate? No. How can you rotate? For example, you see now. How can I rotate? Here you see, this is a double bond, students. Okay, these are the 2 double bonds, right? These are the 2 double bonds. Here 1 chlorine is there, here hydrogen is there, here chlorine is there, here hydrogen is there. So double bond is there. Now can I rotate like this? No. If I want to rotate, then what happens? This both will be getting rotated. See, red is up and pen is, okay, this pencil is downwards, right? Now if I want to rotate, the both will rotate like this. Okay, pencil is coming up. So here to the pen, so red color pen, 2 chlorines are there, and here 2 hydrogens are there. So now only one side, can I rotate like this? No, I cannot rotate like this. See, if I rotate, then what happens? The bonds, see, it's squeezing like this. It's squeezing, right? It's like squeezing. So I cannot rotate. Okay. So if I can rotate, so what happens if I want to rotate? Now both will be coming like this. Both will be coming like this. Again, the 2 chlorines will come one side only. 2 hydrogens will go one side only. So here I can't rotate like this. So this is not interconvertible. They are not non-interconvertible. Means what? This cannot be converted into this one, or this cannot be converted to this one. If I want to convert this one to this one, or this one to this one, I have to break the bond. This bond should be broken, this bond should be broken, then this should be attached to this one, this chlorine should be attached to this one. So, such a type of compounds are called configurational. What they are called? Configurational isomers. Clear? Okay. So, this is a configurational isomer. So, see one material once you see. The isomerism which arises due to the difference in spatial arrangement. Spatial, here chlorine is up, chlorine is down. Okay, spatial arrangement of atoms around the double bond. Around the double bond. So, this is possible only when there is a double bond. Okay. So, around the double bond of carbon atoms. And next one you see, conformational isomers are not interconvertible in normal conditions. So, we cannot interconvert, means this cannot be converted into this one, this cannot be converted into this one. Why? Configurational isomers can be converted, can be interconverted only by breaking and making the covalent bonds. Means to convert this into this one, easily I cannot rotate and cannot convert. But here what happens? Okay, this bond should be broken. Yes or no? So, such type of isomers are called configurational isomers. What they are called? Configurational isomers. Okay, they are called configurational isomers. So, these are examples for configurational isomers. Clear to you? Configurational isomers. Okay. So, which cannot be rotated. Now, if I ask you, then what's the definition of conformational isomerism? Which can be rotated. Which can be rotated easily. So, how can you rotate? If it is double bond, is it possible? No. Here, if the single bond, here what is there? Single bond, if it is there, it is easily to convert. Okay, so easily we can convert. If it is single bond, 2 bonds means what? It will be difficult. 2 pens are there. I just have to know, if 2 pens are there, then it will be difficult. If only 1 pen is there, so it is easily rotatable. For example, what you can write? Example for this one, carbon. Okay, this we are taking ethane. So you can take one chlorine here, and you can take one chlorine here. H. What is this? 1,2-dichloroethane. Right? Here, this is only one pen is there. Okay, so that's what. If I attach something here, I can rotate easily this one. Yes or no? For example, if I attach to some, okay, now I'll take this pen. Okay, so here, okay, here I'm attaching the, see, here I'm attaching this cap, this is, okay, this side I'm attaching the chlorine, and this I'm attaching the hydrogen. Okay, now chlorine is up and this is down. So see, I'm rotating by this one. So this one, red one, chlorine has come down, this has gone up, because there is only single bond. When there is only single bond, I can rotate it as I wish. Yes or no? So I can change this one. How can I change? C, single bond C. Okay. Here chlorine, hydrogen. This chlorine I am bringing here, and this is hydrogen. Okay, what's the name of this one? So 2 carbons means what? Ether. Okay, they are writing ether. Okay, and a single bond is there, ethane. But here you see, first carbon, 1 carbon, second carbon, 1 carbon. 1, 2 dichloro. Okay, sorry, chlorine. Okay, dichloro. So here the name of this one is 1,2-dichloro. This also name is 1,2 dichloroethane. Both are having same dichloroethane. But here chlorine is upwards, here chlorine is downwards. Spatial arrangement, structure same, everything is same. So this is called a conformational isomerism. What we can call it as a conformational isomerism. Did you understand conformational isomerism? Conformational isomerism is possible if there is a single bond. So say just I am rotating this one. this one. Only I am bringing this one. Okay. So like this I can. If double bond is there, you think can you rotate? It is not possible. So that is a configurational isomerism. Did you understand the difference between the conformational and configurational? So once again, see here, conformational means what? Easily rotatable. Okay. So but when it is possible, there is a single bond is there. But here you see if there is a double bond, we cannot convert them. Name is same, 1,2-dichloroethene, 1,2-dichloroethene. But here these both are not interconvertible. Such type of isomers are called, okay, configurational isomers. Did you understand the configurational isomers? Any doubt? Understood? No? Chalo. After configurational isomers, now what is that? After configurational isomers, again there are two types of isomers are there. Okay, so configurational isomers are of two types, geometrical isomerism and optical isomerism. What is that? Geometrical isomerism and optical isomerism. So first we see the geometrical isomerism. Chalo students, geometrical isomerism. Okay, so geometrical isomerism means what? Geometrical isomerism, if you see the same definition, you can see in your material in the page number 93. When each double bonded carbon atoms are bonded to two different groups, basing on their spatial arrangement, two isomers known as geometrical isomers are possible. Now, just now what I told you that we can give an example. Which example? This example we can give. Okay, this example we can give. Okay, so this is an example we can give for the geometrical isomerism. Okay, we can give the geometrical isomerism, that is 1,2 dichloroethene. What we can give? 1,2 dichloroethene. So geometrical isomer is possible. This geometrical isomerism is possible only when there is a double bond. Only there is a double bond. So the double bond, which is between the double bond, carbon double bond carbon is also possible. Carbon double bond nitrogen is also possible. Nitrogen double bond nitrogen is also possible. So these this is possible only when there is a double bond, and between between two carbons, between carbon nitrogen, between nitrogen nitrogen, if it is there, then it is possible the geometrical isomerism. Clear to you, geometrical isomerism? Okay, geometrical isomerism, what? Which are not interconvertible. Remember that, which are not interconvertible. Clear? So once again, see here. Okay, so configurational isomerism, which are not interconvertible. So I'll write for your information. These are not non-interconvertible, and these are interconvertible. In that interconvertible, two types, geometrical and optical. Clear? So geometrical and optical. So this is, we can give an example for the geometrical isomerism. Okay, geometrical isomerism, what, which, okay, this one we can give an example, which are not interconvertible. Now see students here, these are not interconvertible. Okay, this I gave an example. The same example once again I will give. So the example what I am going to give you is 1,2 dichloroethene. Okay, 1,2 dichloroethene. So how can you write the structure? See, now before that I given the structure. How to give the name? I explained you. Now here name is there. How to write the structure also I'll explain you, so you can understand. So eth means what? Two carbons. So I'll write two carbons. 1, 2. Ene means what? Double bond. So double bond. Now 1,2 dichloro. So I think this is the first carbon. This is the second carbon. So 1,2 dichloro. So here 1, 2. Okay. So this is the first carbon, second carbon. So putting him like chlorine. Okay, and chlorine. Okay, and 1 chloroethane. So remaining water. Remaining you should get the hydrogens. So correct? So remaining I should get water, hydrogen. So once again see here. So 1,2 dichloro. So here 1, 2, 3, 4 bonds. Okay, because carbon valence is 4. So 4 bonds, 4 bonds. 1,2 dichloro. So I can put chlorine here. I can put chlorine here. Okay, 2 chlorines and 2 hydrogens. This is one structure. See, eth means 2 carbons, ene means what? A double bond, And 1,2 dichloro means for first carbon, 2 carbons, 2 chlorines are there. So first carbon, second carbon, 2 chlorines are there, remaining 2 I kept the hydrogen. Now, once again I write the structure for this one. Once again I write the structure for this one. Once again, eth means what? 2 carbon, 1, 2. And ene means what? A double bond, double bond. So carbon valence is 4, it can form the 4 bonds, okay, 4 bonds. Now 1,2 dichloro, so the first carbon, second carbon, but here I will put the chlorine, here I will put the chlorine, okay, and remaining I will put the hydrogen. See now. So 1,2 dichloroethane, this also 1,2 dichloroethane, this also 1,2 dichloroethane. Then where is the difference? Where is the difference? Come on, say students, think where is the difference here in both? Both are having the same formula. They given the formula 1,2 dichloroethane to write the structure. I may you can write the structure this type. Your friend is writing the structure this type. Is this which is correct now in this one? Which is correct in these both one? Okay. So the answer is both are correct. If I give to write the structure of 1,2 dichloroethane, then you may write this structure. Your friend may write this structure. Now which one is correct? Means what? Both are correct. Okay, because these both are satisfying this formula. It means 2 carbons, ene means a double bond, 1,2 dichloro, first and second carbon, 2 chlorines are there, first and second carbon, 2 chlorines are there. Okay, so this is a 1,2 dichloroethane. Okay, now, but here where is the difference in the spatial arrangement? Okay, sir, if I ask you, but for example, you are telling that you want your written, okay, you want to write this structure, okay, your friend is written this structure, right? Now, otherwise you think that you are asked your friend to write the formula of 1,2 dichloroethane. So, you are expecting in your mind, you have this structure, you are expecting in your mind this structure, okay, but your friend has written this structure. Of course, this is also correct. Okay, now how can we give the name to this one? Then how can I distinguish these both? Okay, so for that again what we do, this is 1,2 dichloroethane, the same thing. But for this what we do, we write the cis. What we write? Cis, C-I-S. Okay, and for this we write the trans. What we write? Trans. Okay. So now the name of this one is cis 1,2 dichloroethane, and the name of this one is trans 1,2 dichloroethane. That's all. Okay. So what is the cis and trans? See, in the stereoisomerism, especially in the geometrical isomerism, when two compounds, see, formula is same, the 1,2 dichloroethane. Okay, both are same, but here there is a spatial arrangement difference is there. Spatial arrangement difference is there. Okay. To explain the spatial arrangement, again we should give a particular name. Okay. So for that we are giving the cis here, we are giving the trans. So what is cis and what is trans? Cis means what? If the two attached groups, like here chlorines, both are at one side, okay, then we can name them as a cis. What we can name? Cis. And if the chlorine here, so this is upper side, this is downside. Okay, if they are in opposite side, okay, opposite side, then we can say that trans. What is called trans? So now these two are called cis and trans isomers of 1,2 dichloroethane. What are they? They are cis and trans. Okay, isomers, cis and trans isomers of 1,2 dichloroethane. Clear? Any doubt? Come on, students. Any doubt? No. Okay. Now I'll give one more example so that you can understand. For example, I want to write the formula of 2-butene. What I want to write the formula of 2-butene. Chalo, you start writing now. 2-butene I want. 2-butene. Try. Everyone you try. Okay. First how to write, how to take the root word but. But means how many carbons? 4 carbons. So 1, 2, 3, 1, 2, 3, 4. Okay, but. And in means what? A double bond. Where is a double bond? A double bond to two double bond. So two double bonds what? 1, 2, 3, 4. So double bond should be for second and third carbon like this. If you count from here 1, 2, 3, 4. 1, 2 double bond should be here. Like this also double bond here. Like this also double bond here. Okay. So double bond will be for second carbon. Correct? For the second carbon. Right. Now remaining single bonds. So single bond. Now put the hydrogen, so here CH3, right? This is 3 bonds are there, CH, and this is CH, this is a CH3, correct? This is the 2-butene, okay? Now this structure, once again, I'll write here. The same structure I'm writing here, okay? So that is a CH3, single bond CH, double bond CH, single bond CH3. Correct? Right. Now see, the same structure, how can I write? Okay, so here you can see 2 carbons. There is a double bond, right? So see here, 2 carbons. The second carbon, third carbon I am taking. Between the 2 carbon, there is a double bond. There is a double bond, right? Now what I am doing, see, for this carbon, one hydrogen is attached to one CH3 is attached. For this carbon, see, one hydrogen, one CH3. So now I'll put like this. Okay, one hydrogen is attached, one CH3 is attached. Correct? So now this part is done. 2 carbons, 3 plus 1, 4 hydrogens, 3 plus 1, 4 hydrogens, done. Now I'm going that side now. So here double bond over this side. For this carbon, one hydrogen is attached, one CH3 is attached. So here once again see here, one hydrogen is attached, one CH3 is attached. Correct? Now, what's the name of this one? The name of this one is 2-butane. What's the name of this one? The name of this one is 2-butane. Correct or not? See, very concentration is required. Okay? Chalo. So this you understood. Right? Now, once again I am writing the structure of the same one. Once again I am writing the structure of the same. See now. So first I'll take, how did I take the 2? Same I'll take the 2. This carbon and this carbon, 2 carbons I am taking. So 2 carbons. In between 2 carbons there is a double bond. So I am putting double bond. Now for this side I am taking, this side. For this carbon, one hydrogen is there. Okay, one hydrogen is there. And one CH3 is there. So one CH3 is there. Correct? Over. Now that side I am going. So this carbon is this one. For this one hydrogen is attached. One hydrogen is attached. And one CH3 is attached. One CH3 is attached. Okay. So the name of this one is also 2-butane. The name of this one is also 2-butane. Both are 2-butane students. Both are 2-butanes only. Okay. Now where is the difference? Okay. So see now, here the difference here, for both the carbons, methyl group CH3, CH3 at one side and both the hydrogens at one side, correct, of the double bond. But here if you see, for double bond, one side, one methyl is there and a hydrogen. Here methyl is there, hydrogen. Here if you see the 2 methyls are at one side, but here 2 methyls are opposite side. This methyl is that side, this methyl is downside. This is downside, this methyl is upper side, right or no? But here both the methyls are downside only, correct? Any doubt? Okay, so here both the methyls are downwards, but here one methyl is downward, one methyl is upward, correct? So now both are correct only, both are correct only, okay, both are correct only, right? Then what is the name you give to this? So this is also 2-butane, this is also 2-butane. What is the name we can give? Now the name we can give to this one as both are at one side, we write cis here. What do we write here? Cis. And what we write here? Trans. What do we write here? Trans. So now what we can say the name of this one? Cis 2-butane. And what is the name to this one? Trans 2-butane. Over. That's all, students. Okay. So these both are not interconvertible. These both are 2 different molecules. Remember that. These both are not same. These both are not interconvertible. I said not interconvertible means what? I will be taking this only and I am converting into this one. No, it is not possible. These both are not interconvertible. Both are different molecules. Okay, formula same, arrangement same, but only there is a spatial difference. Okay, here both the methyls are at one side, here both methyls are opposite side. So these are called cis and trans. Clear to you? So I have given two examples here. See, two examples I have given. One here, see what is 1,2-dichloroethene. Here two hydrogens or two chlorines at one side, but here they are opposite. So if they are same, cis, and here different, trans. Okay, here also two butane. Here two butane, two methyls at one side, and two methyls are opposite side. So these are called cis and trans isomers. Clear? The cis and trans isomers are what? They are the part of the geometrical isomers. What are they? Geometrical isomers. What is geometrical isomer? Geometrical isomer is a part of the configurational isomers. Okay, configurational isomer. What is configurational isomer? Configurational isomerism is a part of the stereoisomerism. Okay, Stereoism is what? This is a part of the isomerism. So first, isomerism. Isomerism is what? Compounds having same molecular formula but different properties. These are classified into two types: structural isomerism, stereoisomerism. Structural, last class we discussed, chain, position, okay, functional, tatomerism and metamerism, that here. And here stereo again two types: configuration, conformational. Configuration, non-interconvertible. Conformational, interconvertible. Configurational, double bond should be there. Okay, again they are classified into two types: geometric and optical. In this geometrical isomerism part of configuration isomerism. So here we are discussing about this one. Okay, so this is geometrical isomers 1,2-dichloroethene is example, and these both are same, but the thing is that here two alkyl means attached groups are one side, so this is called cis, and if they do opposite side they are called trans. One more example, here two methyl groups at one side, here two methyl groups are opposite side, so this is. Did you understand? Any doubt? No? Chalo. Once you see, close your eyes for 2 minutes and try to recollect it. It's easy, but little, okay, concentration is required. Chalo. So I'm not going to very depth of students here. Some what do you say? Here cyclic structures also there. I'm not going to cyclic structure, that is beyond tier level. Okay, so main concept I'm going to discuss. I'm not going here some examples of cyclic structures. Okay, so this structures you can go through this one, right? Chalo, just 1 minute time I'll give. Once go see this one. Okay, students. So is this clear now? Understood now? Chalo. Now cis and trans. Once if you want to the definition, once if you see the page number 94. You have the boxes once you see the definitions there. Okay, the isomers which has a similar groups on the same side. Similar groups, methyl, hydrogen. So similar groups at the same side of the plane of the double bond are known as cis isomer. What they are called? Cis isomer. Immediately next page you see, next box you see. Okay, the isomers which has similar groups on opposite side. See, methyl in opposite side, hydrogen are opposite side, so they are called trans isomers. Clear no? So this is the definition. Hope you understood this both. Okay, now let us see the properties of cis and trans isomers, page number 96. Okay, so in the page number 94 and 95 you have the structures. You practice these structures. Okay, here I give two examples to you on the board. So these two examples, one is 2-butene and the second one is what? 1,2-dichloroethene. Some other structures you need to practice. Okay. Now properties of cis and trans isomers, page number 96. See students, now properties. Cis and trans isomers have different physical properties such as melting and boiling points. So these two are 1,2-dichloroethene. This is also 1,2-dichloroethene. This is also 1,2-dichloroethene. But whether they have the same physical properties? No. They have the different physical properties. Okay. For example, you see they have the different physical properties such as a melting point and boiling point. If you see the boiling point of dichlorocis, that is 333. Okay. 333 point okay, Kelvin. Okay, 333.3 Kelvin. is the boiling point of this cis isomer. Okay, but here if you see, this is a 320.5 Kelvin. So are they same? Here 333.3, here 320.5. So they have the different melting and boiling points. Their solubilities, their dipole moment, stability and density, all are of different. All are of different. Did you understand? So the trans isomers in general have higher melting point and a lower boiling point. So this is about the properties. Is this clear now? These are about the properties of means they differ in the physical properties. Which type of physical properties? Which properties comes under the physical properties? Melting point, boiling point, solubility, and dipole moment, stability, density. These all are comes under the physical properties. Clear? So that is about the cis and trans isomers. Is this clear? Chalo. Now, students, we go to the now little elaborate now. In the cis and trans, again we go to the little elaborate, that is E and Z isomerism. Okay. So what is that term? E and Z. E and Z. E and Z. Okay, isomerism. What is this E and Z isomerism? So E and Z isomerism are nothing but here cis and trans designations cannot be used for the highly substituted alkenes. Okay, so here these are the alkenes, and here in the alkenes, if you see, for these two carbons, methyl, methyl, okay, methyl, methyl, same are there, and two hydrogens are there. And if you see, chlorine, chlorine, hydrogen, hydrogen, chlorine, chlorine, repeated, okay. But imagine that they have different, for example, C double bond C, but they have different, okay, like here some example, general example I am taking. So here it is A is connected, here B is connected, already C is there, no? Okay, I'll take D, D is connected, here E is connected. So the meaning is what? This is ethene which has a double bond only, but here more 1, 2, 3, 4 more number of substituent groups are attached. Okay, more number of substituent groups are attached, right or no? So they are highly substituted alkenes. They are called what? Highly substitution alkenes. For this highly substitution alkenes, is this cis and trans possible? No. So for this highly substituted alkenes, the cis and trans isomerism is not possible. Okay, for that we use the isomerism called E and Z isomerism. Okay, E and Z isomerism. Okay, how can we use? Okay, I'll give an example to you. The same here, A, B, E, D. Okay, means four different. A is different, B different. Chalo, I'll give some example like carbon, double bond carbon, hydrogen, for example, fluorine, chlorine, bromine. Okay, chalo, like the substituent groups are given here, right? So now these are the two carbons, 1, 2, okay, with a double bond. So this comes under ethene only. But here you see fluorine, hydrogen, chlorine and bromine, right? So what you can give the name to this one is, think this is a first carbon, this is a second carbon. For first carbon, chlorine and bromine are there. Alphabetical order, you can see the bromine. Okay, let's see. Bromine. Okay, so this is called 1 bromo. Okay, and 1 chloro. Okay, this is 2 fluoro. Okay, fluoroethene. The name of this one is what? 1 bromo, 1 chloro, 2 fluoroethene. The name of this one. Correct? So now here, if you see the same structure, I can I write like this? Carbon, double bond carbon, fluorine, I'll keep the same thing, hydrogen. But this side what I am doing, bromine I am writing up and I am writing chlorine is here. Okay. Now what is the name of this one? What is the name of this one? I am taking this as a first carbon, second carbon. For first carbon, bromine is there. So 1 bromo. For second one, chlorine is also there. 1 chloro. For second carbon, fluorine is there. 2 fluoro ethene. Right? So here you see 1 bromo, 1 chloro, 2 fluoro. 1 bromo, 1 chloro, 2 fluoro, ethene, ethene, chalo. Now what's the difference in the name? Is there a difference in the name? No. There is no difference in the name. Both are having the same name. That is 1 bromo, 1 chloro, 2 fluoro, ethane, 1 bromo, 1 chloro, 2 fluoro, ethane. Correct? Now in such cases, what we do? We use EZ notations. What we use? EZ notation. Okay? EZ notation. In the EZ notation, what we see here, what you see here. Okay. Now if 4 different alkyl, 4 different substituents are there, like hydrogen, fluorine, chlorine, bromine, hydrogen, fluorine, chlorine, bromine, okay, are there. Then what we do? We see in such a way like this, you see, for this carbon, fluorine and chlorine are attached. What they are attached? Fluorine and chlorine are attached. Sorry, fluorine and hydrogen are attached. So now we see their atomic number. We see the atomic number. So atomic number of hydrogen is 1. You know that hydrogen is 1. Fluorine atomic number is 9. So write fluorine atomic number 9. Right? Which one is higher? 9 is higher. So 9 higher is upper side and 1 is lower is downside. Chalo. Now we go to this side. Now this side to the other carbon we go. Other carbon you see chlorine. Chlorine atomic number is how much? 17. Right? Chlorine atomic number is 17. And a bromine. Bromine atomic number is fluorine, chlorine, bromine 18 you add, so that becomes 35. Okay, atomic number is 35. So here higher is down. Okay, here higher is up, smaller is down. Okay, lower is down. But here what's happening? Here higher is down, lower is up. Okay, so that is 35 is down. This is 35, atomic number 35. This atomic number is 17. Here atomic number is 1, atomic number is 9. Okay. So here in these two higher is upper side and in these two higher is 35 downside. So highers are opposite in direction. Highers are, they are opposite. Now come here now. Here fluorine is atomic number is 9, hydrogen is 1. Bromine is 35, chlorine is 17. Now in these two higher is 9 upper side and in these two 17 and 35, 35 is higher, that is upper side. So both higher substituents are one side. Here both higher substituents are in opposite direction, right? So then in this case we use the EZ notation. What we call this as a EZ notation. So here we can say that so we can say that here this is E notation. What it is called? E notation. So E means what? Opposite. Okay, E means what? Opposite. Higher or opposite. And this is Z notation. What it is called? Z notation. Z means what? Both are at one side. Clear to you? So here we can give EZ by using this formula, means by using atomic numbers, preferential atomic numbers. So this is called SIP rule. What it is called? This is a SIP rule. Once if you see the material in the page number 97, there is EZ isomerism is there. So there you can see EZ, E and Z nomenclature is used. This system is based on the priority system. Priority system developed and Kahn-Ingold Prelog. Okay, who developed this? Kahn. Okay, C-A-H-N. Kahn. Okay, Ingold and Prelog. Okay, so Prelog. So in this Kahn, C, Ingold, I, Prelog, P. See, this is called SIP rule. According to this rule, the priority wise it is given and higher notations Okay, if they are one side, higher notation, if they are one side, yeah, no, here these are opposite side. Here 9, 1 and 9, here 17 and 35, here higher is 9, here higher is 35. If these both are opposite, this is called E notation. And here 9 is higher, and in these two 35 is here, both are at one side, this is called as a Z notation. Okay, so see here the symbol E is assigned to an isomer in which the atoms or group of higher precedence are in opposite side. Higher is 9, higher is 35, these both are in opposite side. So you can see in the page number 97, small box is there at the complete bottom. So that is okay, the symbol E is assigned to an isomer in which the atoms or groups of higher precedence are given opposite direction. Okay, opposite side. So here that is called E notation. E means what? Fgen. So the meaning of across in the German language. Now turn the page. The symbol of Z notation is assigned to the isomer in which the atoms of groups of higher precedence are the same side. So higher 9 in these two, and here 1735 years or one side. So this is called as a Z notation. Clear to you? So this is a EZ notation. Clear? EZ notation. So EZ notation, this is an example. So here we can give one example. Achha, the same example is given here in your page number 99. Once if you see the page number 99, you have the example like a carbon double bond carbon, double bond carbon, and in that you see fluorine, chlorine. For one fluorine, other one is chlorine, and next side this side is given bromine and iodine, Okay, now that side if you see carbon, okay, so fluorine and chlorine, and but here the I is given up and bromine is given down. Clear? So here you know the atomic numbers. Atomic numbers already we discussed. Atomic number of fluorine is 9, chlorine is 17, bromine is 35, fluorine, chlorine, bromine, iodine. For iodine, what you should add? Fluorine, chlorine, bromine, iodine. So 35 plus 18 you add, so that becomes 53, I think. So this is a 53. Correct? So here now what happens? You see here fluorine is 9, this is 17, and here it is 35, and here it is 53. Okay. So here highest is what? 17. Here highest is 17. In this highest is 53. So both are at one side. Correct? So this is denoted by what? Z. This is denoted by Z. Both are at one side. Okay. Now here higher is what? 17. And here higher is what? 53. The both are in opposite. So this is called E notation. Once you check in your textbook, yes. So Z isomer and E isomer. Can you see here? Z isomer and E isomer. Clear? So this is about the EZ isomers. Okay. So this is EZ isomers. Any doubt in the EZ isomers? Very simple, students. EZ isomers can be used when there is a higher substituent groups are there. Higher means what? More number of substituent groups are there. Then we can use EZ. Okay. And in the EZ also is same thing. If the higher, also here it is given, the atomic number is given as a priority, and according to the SIP rule, so here according to the SIP rule, we see the for carbon which substituents are attached, which substituents are attached based on this. Okay, we can put them aside, same side or opposite side. So based on that, we can give EZ notation like this. If they are in same side, higher, that's called Z. If they are on opposite side, then that is given as E. Okay, E isomer and Z isomer. Clear? So that is about E and Z isomers. Right? Sure. Now general properties of geometric isomers are what? Geometrical isomers already we discussed. They are mainly differs in the physical properties. Where they differ? Physical properties. They differs in the same melting and boiling points, and fractional crystallization, fractional distillation, chromatography. Okay, all these things they are used. This is about the geometrical isomerism. Clear? Any doubt here? So once, just 1 minute, you take the time to check it. So okay, students. So with this we stop. Actually, one more small topics are there, but but it will be prolonged because however we need to do the exercise also now. So with this we stop this class, and in the next class we continue the same topic. But before coming to the next topic, okay, this all you have to learn and practice. How many? Okay, these are all you have to learn and practice and come. Okay, so just for 1 minute, once again, briefly I'll discuss with you. So this one, so that you can understand, and once again we revise. So see us, stereoisomerism compounds having same molecular formula, same structure, but if they differ in spatial arrangement, they are called stereoisomers. Stereoisomers are two types, configurational and conformational. The configurational, okay, they are non-convertible and non-interconvertible, and these are interconvertible, and this is possible for the if there is a double bonds are there, okay, and configuration again classified into two types called geometrical and optical. So in the geometrical isomerism we are discussing. So here this configurational isomerism, and the geometrical isomerism, see, this is possible between the two if there is a double bond between the two carbons, double bond between the carbon nitrogen, double bond between the nitrogen nitrogen. And example you see a 1,2-dichloroethane. So this is also called 1,2-dichloroethane. This is also called 1,2-dichloroethane. But the thing is that here both the chlorine atoms are at one side, both the hydrogen atoms are one side. But here what's happening, see, both the chlorine atoms are opposite, both the hydrogen atoms are opposite. If they are both on same side, they are called as cis, and if they are in opposite, they are called trans. So this is cis isomer, and this was called as a trans isomer. Similarly, one more example, if you see the 2 butane, here for 2 carbon atoms, here 2 methyl groups at one side, here 2 methyl groups are opposite side. So if they are same side, that's called cis. Now they are opposite side, that's called as a trans. So this is about the geometrical isomerism. So in this again, E and Z notation is also there. So here, if you see these 2 carbon atoms which are there, these are attached to the same type of groups, okay. So but if they are at highly substituted groups are there, means like 4 completely different groups are there, then substituent groups are there, that cis and trans is not possible. In such case, what we are doing is we are using another method that is called as a EZ isomerism. So here EZ isomerism can be written on the rule called as a SIP rule, okay. Kahn, Ingold and Prelog. This rule is called. So based on that, we give the preferences to the substituent groups. Okay. Here, how we are giving the preference? In this case, we are giving the preference to their atomic numbers. Okay, atomic numbers. So here you see hydrogen, fluorine, chlorine, bromine. So hydrogen 1 atomic number, fluorine 9. So here highest is 9, and here see chlorine 17, bromine 35. So here 35 is highest. So highest both are in opposite. So this is called as a E isomer, okay. And here you see 1 and 9. 9 is highest up, and 7 35. 35 is the highest. So both are at highest. Both are highest at the highest side, one side. So this is called as a Z notation, E notation and Z notation. Okay. Similarly, if you go to the another compound, so this is another example. So here both the highest are at one side, and both the highest are opposite side. Okay. So these are called as a EZE and Z notation. Okay. So with this we stop. In the next class we continue and we complete this one. Okay. So bye.